Hello students. So our today's topic is magnetism and matter. New chapter we are going to start. So magnetism and matter NCERT section 4.1 to 4.2.2. Okay. So this chapter is in the same unit. Okay, moving charges and magnetism. So it is continuation to that. Okay, we have studied in moving charges and magnetism that the magnetic field is due to the current flowing through the conductors. And one more reason was there. Magnetic field was due to the elementary particles, electrons and other. Okay, so these due to the small movements present within the material. Okay, so that property due to which magnetic field is being produced, we are going to study in this chapter, magnetism and matter. And we are also going to study the magnetic materials, okay, and bar magnet in detail. So let's start. So this is disclaimer. So what is the strategy for comparative exams for this chapter? So focus on understanding magnetic field patterns around different configurations, bar magnet, current carrying wire, solenoid. Okay. Learn magnetic behaviors of different materials. We are going to study the different magnetic materials, which are diamagnetic, paramagnetic, ferromagnetic. You may have studied these type of terms in chemistry also. Okay, diamagnetic, paramagnetic. Okay, so diamagnetic, paramagnetic, ferromagnetic. We are going to study in detail. These are magnetic materials and their real life examples. Connect magnetic properties with temperature effects, Curie temperature and its significance. Practice questions involving magnetic domains and hysteresis curve concept. Okay, so hysteresis curve and magnetic domains. These are also very important topic we are going to study. So practice questions regarding this. And please visit https://forum.pruter.ai for book recommendations and guidance. So learning objectives, after this lecture you will be able to understand the concept of bar magnets. Okay, so the bar magnets is in science lab. You may have seen in science lab in 10th class also, or in 12th class. Okay, so there are bar magnets that are of red and blue color, okay, in the rectangular form. So understand the concept of bar magnets, their magnetic field lines and their relationship to the solenoid in the electromagnetic theory. Okay, so some of you have also may also have done experiments in 10th class regarding drawing magnetic field lines around the bar magnet using magnetic needles also. Okay, so and their relationship to solenoids in the electromagnetic theory. So index of topics that we are going to cover today is, first one we are going to cover NCERT section 5.1, which is introduction of this chapter. Then 5.2 bar magnet, and in 5.2 section there are two subsections we are going to discuss today. So 5.2.1, that is the magnetic field lines, and other section is 5.2.2 bar magnet as an equivalent solenoid. Okay, so let's begin with the introduction part. So in this chapter we will study about magnetism. Okay, starting with the bar magnet and drawing analogies with the electrostatics. Okay, so we are going to discuss in detail about the bar magnet in our initial topics. Then we will move to magnetic materials. Okay, so how magnetism is produced in the materials. Okay, you may have seen the magnet. There is no current flowing through the magnet, but it is showing magnetic properties. Why? Due to some other phenomenon that we are going to discuss in this chapter. Okay, so in this chapter we will study about magnetism, starting with the bar magnet and drawing analogies. We will draw the analogy and we will draw the analogous with the electrostatic also. Okay, we are going to find the magnetic field at axial line of the bar magnet, at equatorial line of the bar magnet, similar to the dipole moment, electric dipole moment. We have derived for electric field at the axial line of dipole moment, at the equatorial line of the dipole. Okay, similarly we are going to we are going to derive the relation for the bar magnets and draw the analogies with the electrostatics. The word magnet is derived from the name of an island, Magnesia. Okay, so magnet is derived from there is one island in the Greece known as Magnesia. So the word magnet is derived from that, where in that island magnetic ore deposits were found around 600 BC. Okay, so there in that island, Magnesia, magnetic ores were found. Magnetic ore deposits were found in very old times, that is 600 BC. Earth itself is a natural magnet, a fact known since 400 BC. Okay, so it is a fact that is known in the very old days, that Earth is a natural magnet. Okay, so it is, but they don't know the actual concept of magnetism of Earth. Okay, they only know that Earth is a magnet that is attracting all the things towards itself, which is due to gravity. Okay, but Earth has magnetism also. Okay, due to which now there is the phenomenon in the poles. Okay, green and green sky. Okay, so aurora, this phenomenon is called aurora. So these green sky in the Norway or in north or south poles is generally seen. This is due to the solar storm. Okay, so the very high means charge particle, high energy particle, cosmic particles when hit the Earth's magnetic field, due to which this phenomenon is generally seen, aurora. Okay, so this is due to the Earth magnetic field. So we will try to find the properties of bar magnet, Earth's magnetic field, and the magnetic behavior of different materials. Okay, in this chapter we will generally see the property of bar magnets, Earth's magnetic field, and magnetic behavior of different materials. Okay, like diamagnetic, which material is, we will classify the material into diamagnetic, paramagnetic, ferromagnetic. Okay, we will see in detail. So some of the facts regarding magnetism are: Earth acts as a magnet with magnetic field lines running from south to north. Okay, so Earth is also as a magnet. Okay, but magnetic field lines are from south to north. Generally, for a bar magnet or for any other magnet, magnetic field lines are from north to south outside the magnet. But for Earth, magnetic field lines are from outside the Earth. Magnetic field lines are from south to north. Okay, so Earth acts as a magnet, but magnetic field lines are running from south to north. So this is the diagrammatic representation. Okay, you can see there is a Earth, and this green line is the geographical axis. Geographical axis means the axis at which Earth is rotating about its axis. Earth is rotating about its axis. Okay, so this is the geographical axis around which Earth is rotating. And this dotted red line is the magnetic axis. Okay, so this is the, so at north side of this axis, so this is North Pole. This is geographical North Pole. This is geographical axis green. This is geographical North Pole. And the pole that is near this, the magnetic pole that is near this geographical pole is known as North Magnetic Pole. Okay, so magnetic pole is very close to this geographical pole, but they don't coincide actually. They are at some distance. Okay, so this axis, this geographical axis and this magnetic axis are at some angle, that is 11.5 degree generally. Okay, so the angle between this magnetic axis and geographical axis is generally 11.5 degree. Okay, that means they both are not at same place but near to each other. So this is geographical North Pole, this is magnetic North Pole, very near to it. Okay, you can see all the magnetic field lines are entering at this point, somewhat at some distance from this geographical North Pole. Okay, similarly, this is South Pole, geographical south pole at which this green line is touching the surface of earth, but this is south magnetic pole which is at some distance from this geographical south pole. Okay, so this is south magnetic pole, this is geographical south pole, and this is geographical north pole, and this is north magnetic pole. Okay, and these are this green line is geographical axis, this dotted line is magnetic axis, and the angle between both these axes is generally 11.5 degree. Okay, so this, and now you can see the direction of magnetic field lines are from south to, so this is arrow is showing the direction of magnetic field, it is from south to north. Okay, so earth is acting as a magnet. A freely suspended bar magnet aligns in the north-south direction. Okay, with north pole pointing approximately to the geographical north. Okay, you can see here is a magnetic needle. Okay, so magnetic needle or a freely suspended bar magnet also. Okay, any magnet, it will suspend itself in the direction of north-south. That means north of this magnet, north of this magnetic needle will point towards the geographical north approximately. Why approximately? Because this magnetic north pole is not coinciding with the geographical north pole. They are near to each other but at some small distance. Okay, not coinciding each other. That's why this north pole will point towards the north pole of the, this north of the magnetic needle will point towards the magnetic north of the earth, not geographical north of the earth. But they are close enough, they are not at very large distance. So this magnetic north of this magnetic needle will approximately point towards the geographical north pole. Okay, that's why it is written approximately to the geographical north, but exactly to the magnetic north pole. Got it? So when we freely suspend the magnet or any magnetic needle, then it will align in the direction north-south, and north pointing towards the magnetic north of the earth or approximately geographical north of the earth. Okay, so this is the behavior. You can see the magnetic field lines are towards this. Okay, so that's why magnetic needle will deflect towards the, in the direction of magnetic field. Okay, so it is found experimentally that magnetic north and geographical north are not at same point. Okay, so it is found experimentally, it has not been derived. Okay, so they have done some experiments with some magnets or any other instrument or apparatus. So they have found that geographical north and magnetic north, magnetic poles and geographical poles are not coinciding with each other, they are at some distance. So like poles, north north, south south of magnets repel each other. Okay, similar to, we will draw the analogous with electrostatics. Like charges repel each other and unlike charges attract each other. Similarly, like poles, that north north or south south. Okay, you may have experimented with the magnets. Okay, there are two pair of magnets that we used to buy. Okay, so they will repel if we hold the magnets, two magnets, and their like poles are brought together, they will repel. If their unlike poles are brought together, they will attract. Okay, so north poles, like poles, north or south of magnets repel each other, while unlike poles that are north or south, okay, they attract each other. Okay, you can see with the help of diagram. So unlike poles is attract. If south and north are close, so they will attract. But if south or north will come closer, they will repel. So magnetic monopoles don't exist. Okay, we have already discussed in the previous chapter also that magnetic monopoles don't exist. Okay, if we break the magnet, okay, if we break the magnet from the half, then it will result in two magnets, but of weaker magnetic strength. Okay, but we cannot say that if we are breaking the magnet from half, then north pole and south pole will get separated. No, monopole don't exist. Okay, they will exist as north and south. So magnetic monopoles don't exist. If we break a magnet, then it creates two complete magnets with both poles. Only its magnetic strength get reduced. So you can see with the help of a diagram. So there is one magnet of length 12. Okay, if we break this magnet into half from the center, it will result in two magnets of length LL. But both magnets will be having north and south pole. Okay, so both magnets will be having north as well as south pole. But because we have cut the magnet, so its strength will get reduced. Its strength will get halved. Got it? So breaking in two parts. So now iron, cobalt, nickel and their alloys can be used to create magnets. Okay, so these three metals, especially these three metals and their alloys can be used to create magnets, permanent magnets. That bar is a permanent magnet. Bar magnet is permanent magnet. Okay, so that means what type of magnets? Two magnets are there. One is bar magnet, that is permanent, and what is temporary, that is electromagnets. Okay, so we will discuss about electromagnets in brief in the end of this chapter. So there are one bar magnets that are permanent magnets, then there is electromagnets. Okay, so electromagnets will retain their magnetism till current is flowing through them. Okay, but permanent magnets are, if we remove the current, okay, they will remain magnetized. They will show magnetic properties even after the removal of current through them. Okay, so iron, like you can see the permanent magnets in your houses also. Okay, so they will retain their magnetic properties. So iron, cobalt and nickel and their alloys can be used to create the magnets. A bar magnet is a rectangular shape. Now we will discuss about the bar magnet. NCERT section 5.2. Bar magnet is a rectangular shaped magnet with two poles, a north pole and a south pole. Okay, a bar magnet is a rectangular shaped magnet with two poles, a north pole and a south pole. So this is the representation of a bar magnet. Okay, so you can see this type of magnet you can also see in the science labs also. Okay, so there is a magnet, it is rectangular shaped. Okay, so one part of this magnet is blue and one other half of this magnet is red. So red half is known as, okay, so the pole that is on the red half side is north pole and the pole that is on the blue half side is south pole. Okay, so this is the diagram for bar magnet. Strength of magnetic field of a bar magnet is characterized by its magnetic moment. Okay, we have discussed what is magnetic moment, but what is magnetic moment in the case of a loop? I into A, current into area. Okay, but in the case of the poles, the formula for magnetic moment is different. It is, we will draw the analogy with the electrostatics. In the chapter electrostatic, what was the dipole moment? Charge multiplied by the length of the dipole. Okay, so similarly here, we will take in the place of charge, we will take the pole strength. Okay, so magnetic moment is defined as the product of the pole strength Qm. So now Q is not charge, it is Qm, it is pole strength. Okay, and distance between the poles. What was electric dipole moment? Product of charge and distance between the poles. Now this is product of pole strength Qm and distance between the poles. So magnetic moment denoted by M. Magnetic moment is denoted by M and mathematically it is defined as M equal to product of pole strength Qm into 2L. 2L is the distance between the poles, where 2L is the distance between the poles of the magnet. So you can see in the diagram. So this is south pole, this is north pole. The distance between these two poles, or we can say length of the magnet, is 2L. Okay, and this is the pole strength. north is taken as plus qm and south is taken as minus qm. Okay, so like we used to take charges in the electrostatic, so minus q charge and plus q charge. Similarly, for poles, minus qm is taken as south and plus qm is taken as north, and distance between them is 2l. And direction of magnetic moment is from south to north, from minus qm to plus qm. In electrostatic, it was minus q to q. Direction of dipole moment is minus q charge to plus q charge. In magnetism, direction of magnetic moment is from minus qm to plus qm, or we can say from south pole to north pole. Got it? Now, direction of magnetic moment for bar magnet is from south to north pole. And you can see in the diagram what is figure 5.1 is given, that is the arrangement of iron filings around surrounding a bar magnet. The pattern mimics magnetic field lines. Okay, so there are we have also seen in the Oersted experiment, there is one diagram representing the iron filings around the current carrying wire. So they will align themselves in the form of concentric circles. Now we will spread the iron filings surrounding a bar magnet. So they will align themselves in the direction of magnetic field lines. So you can see in the diagram also. Okay, so magnetic field lines are in the pattern that is shown in the figure. The pattern mimics the magnetic field line. So pattern of the iron filings around the magnet will represent the magnetic field lines direction or magnetic field line pattern. Okay, the pattern suggests that bar magnet is a magnetic dipole. Okay, so bar magnet is considered as a magnetic dipole. Look at the iron filing shown in the figure 5.1 sprinkled on a sheet of glass placed over a short bar magnet. Okay, pattern of iron filing suggests that the magnet has two poles similar to the positive and negative charge. Okay, bar magnet have two poles similar to positive and negative charges of an electric dipole. Okay, we have also drawn analogy that how we will relate the magnetic dipole with the electric dipole. Okay, since magnetic poles are similar to charges of opposite polarity present in the electric dipole, that's why we are taking analogy from electrostatics. The magnetic dipole moment m equal to qm into 2l of bar magnet is similar to the electric dipole moment pe is equal to qe into 2l. Okay, so in electrostatic we define the electric dipole moment as charge into 2l. Similarly, in magnetic dipole moment we will define m equal to qm pole strength into distance between the poles 2l. Okay, like this you can see in the diagram. Okay, so this is the for magnetic dipole moment and this diagram is for electric dipole moment. So in electric dipole moment we consider minus q charge here, plus q charge here, distance between them is 2l, and direction of magnetic dipole moment is electric dipole moment is from minus charge to negative charge to positive charge. Similarly for the magnetic dipole moment. Now what are the properties of the bar magnet? When a bar magnet is suspended freely, it aligns itself in the north-south direction. Okay, so this is the properties of the bar magnet. When we align or suspend the bar magnet or magnetic needle, okay, freely, it aligns itself in the north-south direction. Why? Because there is due to Earth's magnetic field. So due to Earth's magnetic field is from south to north. Okay, so north of the magnet or north of the needle will point towards the north in the direction of magnetic field. Okay, magnetic field of Earth is from south to north. Okay, so magnetic field lines are towards the north of the Earth. Okay, so north of the magnet or magnetic needle will experience the force in the direction of magnetic field lines. Okay, so north of the magnet will align towards the north and south of the magnet will align towards the south of Earth. Okay, so it aligns itself in the north-south direction. Pole pointing towards geographical north is the north pole. that the pole that is point towards the geographical north is the north pole of the magnet, and the one pointing towards geographical south is the south pole of the magnet. Okay, that we have discussed already. Like poles repel, unlike poles attract. Okay, so for this is also a property of bar magnet, that like poles will repel and unlike poles like north and south will attract. If a bar magnet is broken into two pieces, it will result in two magnets having both north and south pole but of weaker magnetic strength. Okay, if a bar magnet is broken into two pieces, we get two smaller magnets with reduced magnetic field. This is basically summary we have discussed, okay, in the bar magnet. So far we get two smaller magnets with reduced magnetic strengths, and second is each magnet having its own north and south pole. Okay, monopoles do not exist. Okay, like mono charges exist, isolated charges exist, but magnetic monopoles do not exist. Now, section 5.2.1, under the section 5.2. So, definition of magnetic field lines. So, a magnetic field lines is an imaginary curve, the tangent to which at any point gives the direction of magnetic field B at that point. Okay, so it is imaginary lines or imaginary curves. Okay, so tangent to any point on this line will give the direction of magnetic field vector B at that point. Similar to electric field. Okay, in electric field, what is the definition of electric field lines? Imaginary curves or lines, the tangent to which at any point gives the direction of the electric field at that point. Similar here, tangent to which at any point will give the direction of magnetic field vector at that point. So properties of magnetic field lines we will see. First property is magnetic field lines of a magnet or solenoid. Okay, so magnetic field pattern of solenoid and bar magnet is similar. Okay, we will also going to discuss it. So magnetic field lines of a magnet or a solenoid form continuous closed curve. But in the electrostatics, we have discussed that electric field lines do not form closed loops. That's why they are conservative in nature. Why? Because force acting on the charges is conservative. Okay, so these electric field lines were conservative, but magnetic field lines form closed loop, and the magnetic force acting on the charge, moving charge particle, is not position dependent. It is path dependent. Okay, so magnetic force is non-conservative force, and also magnetic field lines are forming closed loops. That's why magnetic field lines are also non-conservative field. This is unlike the electric field lines which begin on a positive charge and end on a negative charge. Okay, so electric field lines start from the positive charge and negative charge. Okay, stop. Then they will not complete the loop. They don't form closed loop. Okay, closed loop means if they are beginning from the positive charge and ending on a negative charge, then they should travel from negative charge to positive charge also to form a closed loop, but they don't do that. So that's why they don't form closed loop, but magnetic field lines form closed loop. They will in outside the bar magnet, they will go from north to south pole, and inside the magnet they will go from south pole to north pole. So that's why they are forming a closed loop. Also in the case of solenoid, magnetic field lines are in the form of closed loops. So it is also shown in the figure. So figure 5.2, the field lines of a bar magnet. This is a bar magnet. This A part is for a bar magnet. This B part is from a current carrying finite solenoid. Okay, and this C part is for electric dipole. At large distances, the field lines are very similar. Okay, so at large distances, field lines are similar. Now, for a bar magnet, you can see from outside the bar magnet, magnetic fields lines are from north to south. Outside the bar magnet, magnetic field lines are from north to south. And inside the bar magnet, they are from south to north. So they are forming closed loop. Similarly, for a solenoid, this is a solenoid, B part. These are windings of the wires, closely wound solenoid. Okay, so they are forming closed loop. Magnetic fields due to the solenoid is also forming closed loop. From this end of the solenoid, this end from where magnetic field is exiting, this is north pole of the solenoid. So magnetic field is exiting from north pole and entering in south pole, and inside the solenoid it is from south pole to north pole. Okay, also in the solenoid I have also mentioned how to find what pole is this. So you have to see that end of the solenoid. Okay, if the current is flowing in the clockwise direction, then it is south pole. If current is flowing in the anti-clockwise direction, then the pole is north. Okay, so we can determine the poles of the solenoid also. So due to solenoid, you can see also for bar magnet and solenoid, magnetic field pattern is similar. Okay, and this is electric field lines due to the electric dipole. You can see for electric dipole, electric field lines are from, this is positive charge, this is negative charge. So electric field lines are from positive to negative, but they are not in the direction from negative to positive. You cannot see any single electric field line which is from negative to positive. All the electric field lines are from positive to negative, so they don't form the closed loops. This is not a closed loop. You cannot say this is a closed loop because they are all in same direction from positive charge to negative charge. Okay, so second property, tangent to the field line at any point gives the direction of the net field, magnetic field B at that point. Okay, so this is a magnet and these are the magnetic field lines. So if we place any magnetic needle on the magnetic field line, so it will align in the direction of the magnetic field line at that point. It will deflect, or it will show deflection in the direction of tangent at that point. Similarly to that thing, you can see in the uppermost magnetic field line there is a magnetic needle and also tangent is shown. Okay, so if we place a magnetic needle at that point, it will align like this. North of that shaded part is north. So north of this magnetic needle will align in the direction of magnetic field at that point, and magnetic field direction can be given as tangent to that point. Similarly, at this point on the rightmost side in the diagram, you can see here, if we draw tangent at this point, it will be like this, vertically downwards. Okay, so magnetic field direction at this point is like this, in the vertically downward direction. Okay, so tangent to magnetic field line at any point will give the direction of magnetic field at that point. Okay, this is the second property of the magnetic field lines. So third property, larger the number of field lines crossing per unit area in a region, stronger the magnitude of magnetic field B in that region. Okay, so where magnetic field lines are closely spaced, that region is of strong magnetic field, and in the region where magnetic field lines are farther apart, then that region is of weak magnetic field. Okay, so you can see in the bar magnet, in the pattern of magnetic field around a bar magnet or solenoid, so at the ends, near the ends, magnetic field lines are closely spaced. So near the ends, magnetic field strength is strong, and outside the magnet, okay, in the middle of the magnet, magnetic field line are farther apart. You can see in the diagram. So near the ends, or inside the magnet, or inside the solenoid, magnetic field lines are closely spaced. So this region is of strong magnetic field. Also at the ends, magnetic field lines are closely spaced. When going away from the ends, magnetic field lines will go farther apart and magnetic field strength will decrease. Also in that region, in the sideway of the magnet or solenoid, there is a very weak magnetic field. We have discussed the reason for the solenoid also. That magnetic field outside the solenoid is very weak and it can be taken as zero. Okay, for a long solenoid. Okay, so magnetic field lines or magnetic field in that region in the sideway of the bar magnet or solenoid is very weak, but at the ends or inside is very strong. So larger the number of field lines crossing per unit area in a region, stronger the magnitude of magnetic field be in that region. Okay, so this is figure 5.2a and b. For example, you can take in figure 5.2a. In this figure, b is larger around region 2. So it is defined that this is region 1. This circle, this loop is containing region 1, and this small loop is containing region this is region 1 and this is region 2. Okay, so b is larger around the region 2. So in this region, magnetic field lines are closely spaced, and in this region, magnetic field lines are farther apart. Okay, so b is large around this region, in region 2, than in region 1. Although it seems that area 2 and 1 are not same. Okay, so it is also visible that this area is large. Okay, we have discussed that larger the number of field lines crossing per unit area. Okay, so area should be same for consideration, but these area are not same, but consider it to be same, then compare the number of field lines. Okay, if we consider these area to be same 1 and 2, even though the magnetic field lines passing through that area will be large, because at close to the end magnetic field lines are closely spaced, or away from the end magnetic field lines are farther apart. Okay, so consider it to be same, then compare the number of field lines in two regions. And the fourth property is magnetic field lines do not intersect. Okay, this was a property also for the electric field lines. Why magnetic field lines cannot intersect? Because if they did, direction of magnetic field would not be unique. So at the point of the intersection, there can be two directions of the magnetic field lines. Okay, we can draw two directions of magnetic field lines at that point. Okay, so we don't want it, or also it is not possible that at some point there is two direction of magnetic field. Only one direction of magnetic field lines at one point exist. Okay, so they do not intersect. If they did, direction of the magnetic field would not be unique at the point of intersection. It is consistent with the superposition principle. Okay, so according to superposition principle, magnetic field is the vector sum of the magnetic field produced by many sources. Okay, but it cannot define that there are two direction of magnetic field. Direction of magnetic field will be unique in one direction at one point. Okay, so in diagram it is shown two direction of magnetic field field is not possible at point P. Okay, so at this P point, so two direction are not possible, only one direction is possible. So bar magnet as an equivalent solenoid, part 1 concept. So this is a bar magnet and solenoid. Figures I have already explained. Okay, magnetic field pattern is same for both the cases, bar magnet and solenoid. Okay, but how bar magnet is equivalent to solenoid, we will now discuss it with the concept and derivation also. Okay, so magnetic field lines of a bar magnet and a finite solenoid are remarkably similar. Okay, so pattern is similar. This suggests that a bar magnet can be modeled as a solenoid. So bar magnet can be considered as a solenoid also, because pattern is same for both the objects, magnet and for solenoid. Bar magnets may be thought of a large number of circulating currents in analogy with the solenoid. So in solenoids there is number of turns, and in each turn current is flowing. Okay, so large number of circulating currents. So we can also think magnet as a large number of circulating currents in analogy with the solenoid. So cutting a bar magnet is half in half is like cutting a solenoid. Okay, so both are similar cases. If we cut the magnet from half, it will result in two magnets having north and south pole, but of weaker magnetic strength. Similarly, if we cut the solenoid from half, it will result in two solenoids having both north and south pole and but of weaker magnetic strength. So if we cut a solenoid, we get two smaller solenoids with weaker magnetic strengths. So magnetic field line at a larger distance from a current loop is identical to the electric field of an electric dipole at a larger distance. Okay, so we have also seen that magnetic field at a large distance due to a current loop. Okay, we have discussed in the previous lecture or previous chapter that magnetic field at a large distance from a current loop is identical to the electric field of an electric dipole at a large distance. Okay, we have drawn the analogy and derived the result also. Magnetic moment M of a planar current loop with n turns, area A and current I is given by, so magnetic moment for a current loop is given by M equal to IA. If n number of turns are there, then NIA. And this M vector is, M is, this magnetic moment is a vector quantity and it is an IA vector, area vector. Okay, so this is a formula for magnetic moment for a planar current loop. Got it? So part 2, derivation. So now we will derive the magnetic field at a very large distance for a solenoid. We have derived it for a loop. So objective, to find the magnetic field at a far axial point P of a solenoid. So consider it as a solenoid. A part, figure 5.3a, calculation of the axial field. So what is the field at axial line outside the solenoid? Okay, so calculation of axial field of a finite solenoid in order to demonstrate its similarity to a bar magnet. Okay, so to draw the analogy with the bar magnet, we have to derive this relation. Okay, so in the figure it is shown that there is a solenoid. O is the center of the solenoid. Length of the solenoid is 2L. Okay, so there is a P point at a distance R from the center of the solenoid where magnetic field is to be determined, and A is the radius of the solenoid. Okay, so consider a solenoid of radius A, length 2L and n turns per unit length. N is not number of turns, it is turns per unit length, that how many turns are per unit length existing. Okay, so per meter, how many turns per meter are there. So the point P is at distance R from the center O. Consider a small element of thickness dx. So we are considering this element of this whole, out of this whole solenoid, we are considering this small element dx. Okay, at a distance x from the center. The number of turns in this element is n into dx. N is the number of turns per unit length, and to find the number of turns in this small element, we will multiply number of turns per unit length n with this length, which is dx, small length dx. So n dx is the number of turns within this small element. Okay, magnetic field at P due to this circular element dx is, now magnetic field due to this element, this small, we have discussed magnetic field due to circular coil, magnetic field at a axial point due to a circular coil, we have discussed in Biot-Savart law in previous lecture. Okay, in previous chapter, from chapter moving charges and magnetism, equation 4.11 for a circular loop, okay, of 1 turn. Then we have considered, there we have considered 1 turn. Now we are considering n number of turns also. Okay, so that formula is dB equal to, that formula was mu naught capital N I A square upon 2 that r minus x was x square plus a was r square in that equation 4.11. Okay, I am explaining. So capital R square raised to power 3 by 2. Now in this equation, that n, capital N is number of turns is in this small section is n into dx. Okay, we have put this. So radius here is a. In place of capital R, radius here is a. And in place of x, the axial distance from the center of the loop. Now from this center of this circular element, this circular element is at a distance x from the center. So from the center, distance of this p point is r. So from this circular element, from the center of this circular element, the distance of this p point is r minus x. Okay, so at a place of x, we are replacing it with r minus x plus radius square a square raised to power 3 by 2. Okay, so after putting the values all in equation 4.11 from this chapter, moving charges and magnetism, we will got dB, the small magnetic field due to this small element. Now we will integrate it. So for a far point, we are discussing for a far point. So for far point, this r, this distance from the center to this p point is very, very large or much greater than the radius of the solenoid and much greater than this x, the distance of this small element from the center. Okay, so it is much greater than a, much greater than x. So denominator will simplifies to what is in the denominator, r minus x square plus a square raised to power 3 by 2. So such that this r is much greater than a and much greater than x. So x can be neglected and this a square can be neglected also. So r minus x will result in r. So it will result in r square plus a square raised to power 3 by 2. Also r is much greater than a, radius of the solenoid. So a square can be neglected also. So it will result in approximately r square raised to power 3 by 2. So after simplifying, it is approximately equal to r cube. So this term is approximately equal to r cube for a very large distance. When this distance is much greater than the radius of the solenoid and much greater than the distance of this element from the center. Okay, so now magnetic field is approximately equal to mu naught n I a square dx upon 2r cube. Okay, so integrate dB over the length of the solenoid from x minus L to plus L. What is minus L? So we are taking this center as origin. So the length of the solenoid in the left hand side of this center O is taken as minus L, and the length of the solenoid in the towards positive x-axis, if we consider O as origin, is taken as L. So we are integrating dB over the total length of the solenoid from minus L to plus L. Okay, over whole solenoid, over whole length. L minus L is 2L. Okay, so from minus L, from this end to the plus L towards this end. Okay, so B is equal to, after integrating dB, so it will become B equal to minus L to L mu naught n I a square upon 2r cube dx. Now mu naught is constant, n is constant, I current is constant, radius of the solenoid is constant, and the distance where we are going to find the magnetic field also we have fixed it. Now dx is only variable. So all the things will come out of the integration and dx will remain in the integration. So integration minus L to L dx. Okay, so over the whole length, so dx will become x. So put the values x, L and minus L. So it will result in 2L after integrating. Okay. So total number of turns. What are total number of turns? N is the number of turns per unit length into, if we going to find the number of turns in the whole solenoid, then number of turns per unit length into the total length. What is the total length of the solenoid? 2L. So small n into 2L is the number of turns in the solenoid. And the magnetic moment is given by M equal to NIA. NIA. So what is the A? Area of cross section of the solenoid is pi A square. A is the radius of this solenoid. Okay. So this N is N2L. So magnetic moment will become N2Li pi A square. Okay. Now what we have derived for the magnetic field, that is mu naught n I a square upon 2r cube 2l. Okay, now we will rearrange this equation and put the value of m. So 2l will come along this n, so it will become n2l, and mu naught I square, we have to form this pi I square in the numerator. So we'll multiply this equation with pi and divide with pi also. So it will become pi a square upon pi also. Also we are going to multiply it by 2 by 2. Dividing it by 2, multiplying it by 2. So it will become 4 pi in the denominator, and in the numerator there is 2. 2 will appear. So mu naught by 4 pi, this constant is sorted. So 2 into n2l and I, pi we have multiplied in the numerator and denominator, will become pi a square and upon r cube. So n2li pi a square, this whole term will become magnetic moment. So it will result in mu naught by 4 pi 2m upon r cube. Got it? So this is the magnetic field at axial line at a very large distance from the center of the solenoid. So field on the axial point is given by BA. Axial point is equal to mu naught upon 4 pi 2m upon r cube. So m is the magnetic moment. Okay, mark it as 5.1 equation. Okay, above expression also represents the far axial magnetic field of a bar magnet. So this formula is also same for the bar magnet. So for represent the far axial magnetic field of a bar magnet which can be obtained experimentally. Okay, so this formula also represent the magnetic field at far axial point of a bar magnet also. So what is the conclusion? Does a bar magnet and a solenoid produce similar magnetic fields? And we can say that bar magnet and finite solenoid closely resemble each other. Okay, so both the bar magnet and the solenoid resemble each other. Magnetic moment of a bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic field. Got it? So what is equatorial field? We have derived the relation for axial field. Now we will derive relation for equatorial field with the analogous with the electric field. So electric field at a distance r in the equatorial plane of an electric dipole. In electric dipole, we have also find the electric field at the electric field produced by dipole at the equatorial line for a short dipole. So which resulted in EE. EE is means electric field at equatorial line, which was magnitude of this electric field at equatorial line was P upon 4 pi epsilon naught r cube. Now if we replace this 1 by epsilon naught with mu naught and P with M, this electric dipole with magnetic dipole, and this E with B, then we will get. So we take analogy from it to get the magnetic field at a distance r in the equatorial plane of what is equatorial plane? The plane passing through the equatorial line. Okay. So we will take the analogy from it to get the magnetic field at a distance r in equatorial plane of a bar magnet or an equivalent solenoid. So BE will be equal to mu naught by 4 pi m by r cube. So for equatorial line, for a point lying on the equatorial line, magnetic field due to the magnetic moment or due to the solenoid bar magnet will be this mu naught m upon 4 pi r cube. Got it? So let's move on to the summary, what we have studied today. So magnetic materials tends to point in the north-south direction, like magnetic poles repel and unlike ones attract. Cutting a bar magnet in two leads to two smaller magnets. Magnetic poles cannot be isolated. So consider a bar magnet of length L and magnetic moment M at a distance r from its midpoint, where r, the distance is much greater than the length of the magnet. Then magnetic field B due to this bar magnet is given by B equal to mu naught by 4 pi 2m upon r cube. This is along axis on the axial line, and magnetic field on the equatorial line is minus mu naught m upon 4 pi r cube. So we have found the formula. We have seen that B is equal to mu naught m upon 4 pi r cube. This negative sign was not there in the previous slide because we are dealing with the magnitudes. But when we are taking the vector sign also, we have taken the bold sign of magnetic moment and magnetic field. So in vector form, the magnetic field at the equatorial line is in the direction opposite to the magnetic moment. Okay, that's why negative sign appears. So B is equal to minus mu naught m upon 4 pi r cube. This is a vector form along the equator when point is lying along the equator or equatorial line. Okay. So there are some practice questions you have to practice yourself. What is a bar magnet called an equivalent solenoid? Why is a bar magnet called an equivalent solenoid? Explain with the simple diagram. If you break a bar magnet into two pieces, then will you get isolated north and south poles? And what will be the magnetic properties of each piece? Explain your answer. Two bar magnets are placed near each other with their north poles facing each other. Describe what will happen and explain why. Okay. So thank you, but we have to do the DPP section also. So first question, which property distinguishes magnetic field lines from the electric field lines of an electric dipole? So you can write your answer in the comment section also. When a bar magnet is cut transversely into two pieces, what is the result? The torque tau on a magnetic dipole of a moment m in a uniform magnetic field B is given by. So what is the torque? This we have discussed. This is not relevant to this topic, but we have discussed earlier. The magnetic potential energy of a dipole in a magnetic field is minimum when angle between m and B is. Which configuration of two magnetic dipoles represents stable equilibrium? Okay, it is m cross B, but this tau is not bold. So there is a misunderstanding. This tau should be bold for this m cross B. Otherwise, it is only magnitude m sine theta. Okay, this is a confusion. Okay, other options are correct. Okay. Thank you then. I hope you enjoyed the session.